And let me start recording the session. So how is everything after 1 week? Guessing everything is tired? Yes. Yes, me too. So that's the reason I think this happens to me when I haven't slept in many days. My body always has me to stop. So yes, so probably I only need to sleep early. Okay, Lupita, yes, you need vacations again. I need vacations, period, which is really sad. Yes, I know. Pam, pam, pam. So let me, this is sección 3. And 1, 2, 3. Okay. Yes, but I don't know if, well, I haven't told you this, but I remember I was talking to somebody who graduated last May, and he was telling me, like, Mauricio, when I realized that this was the last vacation that I ever had, like as a student, he kind of got into a like big depression for a couple of days, and I was like, yes, it's not gonna be the same. Of course, we have vacations, we get vacations and days off, but it's not the same as when you're a student. So I don't want to sound like an old guy, but please enjoy it. Enjoy it while you're still at UTLAB. Mhm. Mhm. But it's also fun because you start becoming more independent. You get your own money. You realize that most of that money is going to go away paying bills, and yeah. But it's a good transition to adulthood. Okay, so let's continue with this session. So last session, yes. Also, I don't know what happens with my tablet when I'm with this session and the previous one, because on Tuesdays and Thursday the tablet is working just fine, but hopefully tonight is going to behave. Okay. Okay. So the last example that we discussed last session was this. Given that we have force of mortality expression, this one, we wanted to estimate these three probabilities. And again, I just didn't finish it. Did you do this estimation or not? You didn't have to, but I don't know, probably somebody worked on this. Yes, wonderful. Mhm. So let's just go really quick through this example. Let me. Mhm. No, it's not this. Oh no, yes. Well, I don't have every single step, but just to double check, Lupita, you should get 30, 52, 66, or yeah, whatever that number is. It kind of sounds, yeah, it seems like it's almost the same. Mhm. Mhm. Okay, if you have questions, you can ask Lupita. Now you can ask me on office hours. Okay. Now, let's. So this is really easy. This is really straightforward. But these expressions or these type of expressions are expressions that you're gonna find while you work on the problems that you have to be working. Now you can start working on those things, and that to estimate probabilities of surviving and probabilities of not surviving and all these things. So there's nothing different in this example from the example that we had before. This is easy because we have 70 years here, and we are asked to estimate this probability for somebody who's age 70, so that's fine. And according to our formulas, the probability of somebody who's 70 surviving to age 90 is e to the negative integral between 0 and t is 20 for this expression, right? The only thing here is that since we have this this function in two parts, we will have to break this integral into two parts. The first one going from 0 to 5, because this is the limit that we have here, 0.01. And the second one going from 5 to 20, 0.02 ds. And of course, you can integrate these values without big problems, right? So, okay. Let me delete this 5 because it seems like this is kind of together with the 0, but it's not. 5. Okay. So again, you're gonna find a lot of examples or problems that have this perspective, because again, we cannot assume that the force of mortality is the same for everybody. In this example, they are changing the impact based on the time that we are expecting this person or this individual to survive. So in reality, we would need at least, I don't know, we could break down this from age 0 all the way to age, to the last age in our population, using intervals of 5, 10s, or whatever. So again, I am not going to ask you to work with an integral with a function of, I don't know, 21 segments, but we could if we wanted to. Okay. And this example is really interesting as well, because as you can see here, we only have x. So this function has to work for any given age. So we don't have issues with the limits for the integral. And since we don't have any value here, what is the value of t? 1, exactly. So this means t equals 1, okay? So essentially, we want to estimate this probability, essentially the probability of a person whose age x dying before age x plus 1. Okay? It's convenient that we remember that is the complement of the probability of surviving, and we know how to estimate this probability, right? It's just 1 e to the power of nu. I'm just gonna change the variable to t. So I could use, and this is important. Let me change. I could use this and integrate from 0 to 1, or I could change variables and integrate from x to x plus 1. This is exactly the same because I'm just here changing the limits of my integral. And again, these are things that you have done before so many times that I'm not gonna even stop explaining these things. But remember that if I change the variable here, I need to change the limits, the integration limits, okay? Yes? So if you solve it in like both scenarios, here you will have x plus 1 and x plus 0, and here you have x plus 1 and x plus 0 when you substitute the value of the variable, okay? And yes, I am not going to solve this, but again, I'm just gonna give you the final solution. So if you want to practice more, you can do it. So again, it's up to you to get this value, which is not that complicated when you see the integral that you have there. Okay. So why am I in a hurry for to discuss these things? Is because yes, these functions work a lot, but in actuarial sciences and like demography and some other fields in statistics, we have developed or we realize that there are some expressions for survival And again, remember that this survival is the same as this for human mortality. So these are called mortality laws or analytical mortality laws, or essentially, but these are mortality laws. If you're talking with actuaries, you mention one of these, everybody should understand what you're talking about. So the most common are the MOAF, and pardon my French because I am not, I don't know French, so you can help me with the pronunciation, but it's not the moivre because before I got here to lab, they were saying the moivre, and I was like, no, at least try, okay? So it's the MOAF. Then this is really simple, a simple function. It's not that complicated, but SOA loves using this mortality law in the exams. So that's the reason we're going to spend a few days talking about the MOAF law and the implications that this has. Then we also have Gompers and Mayhem. I don't know if you discussed Gompers and Mayhem in your Teoría del Seguro class, but these are essentially the gold standard when we are trying to model human mortality. Gompers is mostly used, well, is used the most in statistics and survival analysis. Mayhem is used more in, essentially actuaries do use Gompers and Mayhem essentially interchangeably. We don't pay attention to, well, of course we pay attention to which one we are using, but again, the for us is the same. Of course, the requirements that each one of these functions have is different depending on if we go with Gompers or Mayhem. And then we have Weibull and geometric. These are the Weibull distribution and the geometric distribution that you probably have discussed these distributions in statistics or in your statistical inference class. If you haven't discussed these two, we already have a tema selector for your last semester when we are going to recover some information from non-life insurance, and this Weibull function is going to pop up because Weibull essentially and geometric are used for non-human populations. Just if we're modeling cars or whatever, that's when we find these two. So in this semester, we are not going to use these two. Okay, so now, what is the big deal about these laws of mortality? The first one is the MOAF, and I don't remember the exact year when this guy developed this expression, but it was in the 1700s. And this essentially what he said was, okay, let's assume that deaths are going to be uniformly distributed throughout this interval, 0 and omega. Be careful, this is not a W, this is omega. The last letter of the Greek alphabet, so we use omega as the last value for the age in our population. So essentially, nobody survives beyond omega, okay? And this is important. If you ever say W, I am going to judge. In this class, I will exterminate that, that critique. Probably in the future, I will just do it internally. We'll do it internally, but again, be careful with this. So again, we have H0 and H omega, and we assume a uniform distribution of deaths, or essentially a uniform distribution of the way that our population is surviving. So he developed this expression for force of mortality, which is not a straight line at all. It's essentially, if we have omega being 100, and then let's do a small plot. I am recording this, right? Yes. So if we have here omega, and here we have, well, any value of mu x, this is 0. When h is 0, omega, let's say that is 100, is a big value. 1 divided by that is going to be really low. And as we start moving, this thing is going to go all the way to infinity, because essentially we could go all the way to omega in h. So of course, we will have 0 here. So this is the pattern that force of mortality follows. And when it comes to survival, and you can see how essentially I am getting the survival function from here, it's just the same rule that we had before, the exponential, the negative integral from 0 to x, or in the next slide I have from x, well, from 0 to t. of this expression, and then just integrating this, conveniently we get this thing. And this is the shape of what? What is the shape that this function has? Who can tell me the shape of that? Come on. Who was your geometry teacher? Exactly. Thank you, Michelle. It's just a straight line. Why? This is the slope. The slope is -1 divided by omega. This is the slope, or pendiente, and this is the intercept, right? So it's just a straight line. And remember, this is a survival function, so we know also that when we have h being 0, this is 1, yes, is immediate from there. And when x equals omega, this is 1, 1 subtracting 1 is 0. So essentially, this is a straight line. Okay, from here to there. This is sxt, or s0x. So, of course, this is a really a big and a strong simplification of mortality, because we know human populations don't follow this pattern. Essentially, we know that at the beginning, the first days and weeks of life, a lot of babies die, but then essentially mortality levels off, and it reaches the minimum value around 5 and 7 years, and then it starts increasing, but it has a small increases, like something, something like this, and then at the end it has to go up. Okay, so essentially, if we have a lot of people dying at the beginning, it should go down, and then kind of following up here, and then falling at the end. But this is useful, and again, SOA loves using this function for their exams. So again, it's really convenient for us to discuss this function. Okay, and the general version for this law of mortality is just adding x minus t in the values here. Before it was omega minus x, and now we have the another value of t. And the survival also includes x down here and t up here. So these are formulas that my advice is start working on your cheat sheet. Essentially, the formulario, the ones that you're going to be using. Of course, for the exam, you will have access to all these things. I don't care, because the way I see these things is life is an open book. It's an open book exam. So you can come here and double check all the formulas and stuff, but it's easier if you have everything together in one page, so it's easier for you to find it. Okay. So these two are really going to be useful. Okay. So let's see what we do with when we have the Moab's law of mortality. So just with this example, here we have that the force of mortality for a person who's age 30 is mu x equal 1 divided by 100 minus x. And now we want to calculate or to estimate the probability of this person age 30 dying on his 70s, essentially between 70 plus whatever epsilon we want to use, all the way before 80. So essentially what we have there, and I am using this on purpose so you can start again practicing the notation. So we will have this. The person is 30 years of age, and we want this person to survive to age 70 and then die before age 80. Okay, so essentially we want this person to survive 40 years and then die before 80, so 10 more years. Okay. So we have solved, we had an example like this before, right? So what we need to estimate is then the probability of this person surviving from age 30 to 70, and then subtract the probability of this person surviving from age 30 to age 80. And since we have the MOABs, is really easy. So it's the general version of this. So the probability, which is this, is 1 subtracting t divided by omega. Okay, so it's 1 subtracting t. T is 40. What is the value of omega here? Exactly, 100. So omega equals 100. Maybe 100, and h is x. And then we're going to subtract. Now it's 50, 100, which is really easy to estimate. So this is 70, 70, 40, 70 again, 70, 50. So we have 30 and 20, and then we have 70, so it will be 1/7. Okay, so you can see this is, sometimes I even call it lame, but I shouldn't do that. I shouldn't call the Law of Mortality lame, but it's really straightforward. It's just pay attention to the value of omega that you have, and then just replace the values here. Why? Because you can follow why 40 and 50, because we want this person to die between age 70 and 80. So if we have the person being 30 years of age, I want this person to die during her or his, this is a guy, 70s. So I want the person to die here, right? So first, what I want to do is this person to survive all the way to 70, which is 40. Okay? And then I want to subtract the probability of this person surviving all the way to 80. So to 80, even though here I'm telling you 10 more years, if you draw this, yes, this is 10 years. But from age 30, this would be 50, 30. Is that okay? Thank you. So we're gonna be, if I don't know if you already started working on the problems, but if you start working on these problems, you're gonna find a lot of these with the MOAB, because I want you to practice this a lot. Well, it's not a lot. I think for week 1, I think there were a total of 12 problems, but again, a couple of problems was like, say if this is true or false, and things like that. Well, at least last year, they didn't hate me at the end of the year, so I'm guessing it was okay. So let's move to more interesting laws of mortality. And now let's start talking about Gomper's law. Well, Gomper's law. Essentially, what Gomper said, when this was in 18 something, I don't remember, I think it was 1843. Essentially, Gomper goes with, okay, we cannot use this assumption that the survival of the population is a straight line, or essentially that mu x, mortality follows a uniform distribution. So this is not working. However, he said, okay, but let's assume, if you pay attention to this thing here, he said, okay, let's assume that if I take the log of this, I can get a straight line. And again, we are actuaries, we love working with transformations. So he said, okay, so let's get the natural log of this expression and say that this is actually a straight line. Again, this is alpha plus beta x. Okay, straight line, traditional straight line. And if we want to estimate mu x, we just get the exponential from like both sides, and using these substitutions, calling b, e to the power of alpha b and e to the power of beta c, we end up with this expression, which is Gomper's law of mortality. Okay, so you can see it's not a straight line because we have hx as a power, but it's not that complicated. We just work on a transformation and we can get a straight line. Okay, so what do we need? Essentially, if we have this approach, we just need values for b and c, and we can estimate the value for mu for any given age x. And a lot of the problems that we have, or a lot of the time when we are working, if you are actuaries working on estimations of mortality, you're going to be spending that time estimating these values. Of course, now we have software that can help us with this, but a lot of people are still developing more and more and more things for Gomper's law. Okay. Now, when we get the survival function or the probability of surviving, we just follow the same perspective. It's just e to the power of the negative value, the interval between 0 and t of this function. Again, now I'm just adding the plus s because this h is going to be varying between 0 and t. And again, since we have a lot of information here, we will end up with this expression. Okay, you can try it. You can work again. It's not that complicated. It's just the integral of c to the power of x, and you should remember. Well, you always have this problem in calculus. Well, the first time that you see this is with derivatives and then with integrals, so you can work these things. But look at the expression that we get. It's not that easy. Well, of course, for us, it's not that complicated. We have seen worse, and we will see worse. But it is for most people, this will represent some issues. Okay. Again, how are we going to estimate C, and how are we going to estimate B? That's the big question, and that is something that we're going to do tonight, at least for the Gompers. Now, before moving to that example, let's talk about Mayhem. Mayhem, essentially what he did, he just improved. By the way, the meaning of these parameters, C is just mortality that comes with age. As you can see, C is associated with age, and B is like the randomness of mortality. Again, this is the explanation that we have for these parameters. So Mayhem came and he said, okay, yeah, kind of looks good, but I think we can improve that. And let's add another parameter, a third parameter in this expression, and this essentially is going to be a constant force of mortality. Essentially, mortality is always going to be around, even if you take care of your population in a crazy way, and even if you do everything that is on your hand to avoid mortality, there's always one presence of mortality that is there. Okay, so he added this constant parameter, but again, it's constant in the transformation. Okay, it's a linear transformation that we have here. Well, not a linear transformation, it's a transformation to turn this expression into a linear expression. Okay. And again, if we integrate this expression, we get something pretty similar to the previous one. And again, if I have this, I just need values for A, B, and C, and some other information, such as what is the age of my individual, how many years I want this person to survive, what do you want me to estimate? And we can come here and estimate these things. If we have 3 parameters to estimate, we need 3 points, right? 3 observations in time, or in 8 different ages. If we go with Gompers, because we have 2 parameters, we need at least 2 observations. Okay? And this is, again, basic things that you have done before, and you actually have used the general solution for these things in your theory of matrix classes. That every time that I start talking with the professors and they start telling me what you're learning there, it just gives me the chills, because I didn't really love that class when I was studying. But it's a really useful tool. Okay, so let's solve one example. Oh, by the way, how do these functions look? And they look pretty similar. Again, here we have omega. Here we have, let's plot this survival. This is 0, and this is 1. So the way these functions look is something like this. Which, if I ask you, okay, how are human populations dying, and you see this, it makes sense, right? That the proportion of those surviving, like 0 times 0, is going to be 1, because they're already here. We have this drop at the beginning, and sometimes with Gompers we don't see this drop. With Mayhem we can see it, but essentially kind of levels off. But of course, remember that the only requirement for this function is being a only requirement. The 3 requirements is 1 here, is 0 here, and it's a non-increasing function. So it can be constant, but it cannot go up. Okay, and yes, yes, I think we can assume that this is non-increasing except for this part, but again, I'm doing my best. So and by the way, we're going to use these expressions to estimate life tables. And yes, these expressions are expressions that are used. I have some students from your generation working with me in the honors program, and with a couple of them, we're going to be estimating this for Mexico. So it's a really nice thing to do. Now you see why actuaries need all the mathematics that you had before. Okay, so let's estimate. Well, let's work with this in this example. Okay, we have that mortality for a person who's age 20 follows Gomper's law of mortality, and we know that we have these two values. Mu of 30 is 0.001, mu of 80 is 0.15, and we want to estimate the probability that a person age 20 dying before, surviving to age 70. Okay, so that is the probability that we have here. Remember that this is the age and the time we want this person to survive. So 20 plus 50 is 70. Okay, so what are we going to do? Let's start with what we have. We know that force of mortality at age 30 is 0.001, and this comes from B, C to the 30. By the way, the C is a lowercase c, but I have issues like drawing it. But yes, C in both expressions is lowercase all the time. Why? I don't know. So this is where this is coming from. Okay. Essentially meaning, well, no, let's leave it like that. And we know that at age 80, this is 0.15, and this comes from this expression. Okay? Which means that the natural log of 0.001 equals to the natural log of B. I'm not going to use parentheses because it gets really packed here, plus 30 times the natural log of C. And we also know that the natural log of 0.15 comes from this and I say 80. Okay. So what do we have? We have two parameters to estimate, and we have two equations. So we know how to do this, right? So let's call this A and this B. So let's take B plus the, well, let's get the difference of these two, which essentially means that we have, well, the natural log of, well, let's do it step by step, because natural log of 0.15 subtracting the natural log of 0.001 equals, we get rid of the B, we have 80 and 30, so we end up with 50 natural log of C. And we know that the difference between the two logs is the division between these two numbers. So essentially this means that C equals to, let me do it from here, natural log of, no, you see, this is the reason I should go step by step. So the natural log of 15, well, no, 0.15 divided by 0.001 is natural log of 150. Yes, 1, 2, 3, 1, 2, 3. And then we divide this by 50, and this is the natural log of C, which means that C is E to the power of natural log of 150 divided by 50. Okay, so now we have the value for C. Now what can we do? Well, then let's replace this in the second second expression. Okay, now which means the natural log 0.15 equals the natural log of E plus 80 times, as you can see, is the natural log of E to the power of, but then it's going to be log of 150 divided by 50. Which essentially means that E equals, let me see, I think I'm just gonna leave it like this. I'm too lazy. E to all these things. Okay. So can you give me the value of C with 4 or 5 decimals? Okay, thank you. So C, thank you. So we have 3 confirmations. That's enough. Thank you. 1.1054, and B, which is a little bit more complicated. Can you give me this value? 0.00049. Okay, yes, I think yes, it has to be a really small value. 0.00, how many zeros? 4 or 5? 1, 2, 3, 4. Thank you. 4, 9. And of course, if you work on these things in, I will use Excel so I can have lots of decimals, or your amazing calculators that you have. So now that we have B and C, we can just estimate the probability that we wanted to estimate, right? Which is going to be E to the negative value of, I'm just going to write it here because it's too complicated. C to the x is 20, times C to the 50, and everything divided by the natural log of C. And if you do this, you will get 0.57937. Okay. And again, I saved all the decimals in my calculator, so probably if you just work with these two, you're gonna have a difference in this thing. So as you can see, this gets more interesting when we have expressions that are not like straight lines. But of course, they are more demanding. They are more, well, time consuming in general. And we need to have at least some information regarding like 2 points in time for Gompers. And if we were to estimate Mayhem models, we would need at least 3 observations in time. Okay, which is sometimes not that difficult to get, but it's not like we are getting those things from, I don't know, in the inside of a cereal box. So it's a lot of work to get that information. Okay, questions in this example. Essentially, this was just solving a system of equations. So questions here? Okay, great. So we have right now a random variable, we have lifetime distribution, we have survival function, we have probabilities of surviving. But since we started this class assuming that the future lifetime of an individual is a random variable, we get an expression for that. We can get that expression for that. That's easy. But we are actuaries, so we need to get more information than that. So let me go to the next. So we are going to estimate moments for our random variables. And this is the reason I told you, you need to go back and study your stochastic models lessons. But again, we're just going to use the basic of these things. I think if I were to take one exam of the exam that you're going to take this semester, I would probably fail. Well, if I don't study. But anyway, so let's estimate these moments. So again, it all comes from the fact that future lifetime is a random variable, and this is expressing the remaining time of life a person age X has until his or her death. And again, we want some basic information, not only the density function, because that's something that we know we can get, but we also want the mean and the variance. So essentially, remember that in order to estimate the mean, we are going to get the first moment of this function. And to estimate the variance, we need to get the second moment and then get the difference between the second moment and the square value of the first one. Okay? So let's use this traditional approach of moments of random variables to estimate the mean and the variance. However, since we are in actuarial mathematics and we love naming things using special names, the first moment, essentially, which is the expected value of the future lifetime of a person whose age X, is called the complete expectation of life, or the complete life expectancy. And this is something that probably you heard before. For instance, well, right now, well, yes, the mortality information is already out. So I don't know if the news is already, well, the news are talking about this, but if a few weeks ago from the US, they were saying, okay, because of COVID, we lost 4 years of life expectancy. And because of this, we lost this many years, and so on. So this is an indicator that we use a lot. In this class, we're going to use it for estimating things that we want to estimate for an insurance company. In demography, for instance, we spend a lot of time trying to estimate this value for life expectancy. But it's a different one, but it's essentially a close relative of this. Okay, and it makes sense. So if I want to remember that the life expectancy is on average, because it's the first moment, is on average how many years of future lifetime a person has. Which for me, it makes sense that is life expectancy. So I am expecting this person to live this many years. We usually go, when we're comparing countries, we go with life expectancy at birth. Essentially, if a baby is born right now, on average, how many years I'm expecting this baby to live? And this would be the age at which this baby is going to be dying, right? But we can get this life expectancy for different values. For instance, at age 65, because some of you, I don't know, but at least right now, from the last year graduates, I think 2 are working on pensions. You're going to be doing estimates of life expectancy at age of retirement, essentially at age 65, because you need, as an insurance company who has pension plans, to estimate on average how many years you're expecting to pay the pension for your policy holders. Okay, so yes, it's something that we use and we can estimate for any given age. So just remember that from last session, we found out that the density function is essentially the multiplication of the probability of surviving times force of mortality, or essentially force of mortality was density function divided by the probability of surviving. Okay, so we use Sx, but essentially it's the same. But we also know that force of mortality was 1 divided by the function times the derivative of the function. And here I'm just since I have the same value here, I'm losing the 1 divided by the function. So this is another expression for density function, okay? So what do I need this? Because we're going to get the first moment of this variable. So life expectancy or complete life expectancy has a small o on top of the e, is the expected value of this random variable, which you all remember that is the interval from 0 to infinity, because we have an open interval. And it doesn't matter if we know that the last person is going to die at age 0, at age 100, then we will have zeros, so that doesn't affect our estimation. T times the density function. Again, this is basic stochastic models. And here I'm just replacing this function with the multiplication of probability of surviving times the force of mortality. We can go with iteration, using iteration by parts. Essentially, la cabecera del informe, if you remember that with that approach. Don't tell the mathematicians that I use that expression, because they hate it. I don't know why. It's really useful. So let's change, essentially, because we already have the expression for the derivative of the second part of the function. Let's break it down into these two components. Okay. So come on. So essentially, we need to integrate this t times the derivative of the survival function and the negative value that I had before here. Here, I already have it here. So I can take the negative value out of the integration. And this is this, or the first variable, times the integral of the second one, but I have the integral of the derivative, so it's just the function evaluated in the limits. Subtracting the second one times the derivative, of the first one, which is 1, because it's t. Yes, I think I said it, well, probably. You remember the exact words. And it's interesting because remember that we have a condition that when this equals 0, this t is 0, so this goes to 0, that's fine. And we also have the condition for survival functions that when we have values going to infinity, this goes to 0. So essentially, this part here goes to 0. And we end up with the negative and negative, so it's just a positive value. And then we get this simplified version of life expectancy, which for me is really interesting, because if I am asking, okay, so what is the life expectancy of somebody who's age X? Essentially, what I'm doing is, okay, let's estimate the probability of this person surviving to each one of the possible values of t, and then add all those probabilities, and we will get the expected number of years this person will live, which is really neat. Okay? And the second moment is exactly the same, but now we add t to the square, because that's what the definition of second moment, and we follow the same perspective. And again, this part goes to 0. And here we end up only with these two, because the derivative of t squared is not 1, it's 2t. So we have this expression for the second moment, and using this, we can get the variance, which is the second moment, and then subtracting the square value of the first moment. Okay, so this is, again, we're just calling life expectancy, complete life expectancy, to the first moment. The second moment doesn't get a name, and the variance doesn't get a name either, but the first moment is complete life expectancy. So questions here? So you can see, this is the mathematics that we're going to be using. So don't worry, just practice your integrals, practice when we change limits of integration. And I think right now I have one example of that we're going to change the limits of one integral. So we need to be ready. Let me see, where is it? My example. This is like tables, no moments. Okay, here. So let's work with this example. And it's the same function that we had before, as you can see. The same function that we used for the first example and the second, right? So we have this future lifetime, and we want to estimate life expectancy for somebody who's age 30 and somebody who's age 80. Okay, so the first thing that we do is, because we are not going to work with this, we get we get the survival function, which is, sorry, let me use x. X, which is xp0, and this is 1 x divided by 120 to the power of 1/6. Okay, so even from now we can see that we will have to change this expression, because here we have the function. Remember, we have the function at h0 and we want the function at h30 and 80, but that doesn't matter, or it's not a big problem. It's just well, remember that dpx equals true. I can go with either well, x plus t factorial notation 0, and x, which is in the other notation that we have, x plus t by x, right? So let's do this. Whew. So if I want to get this, we will have 1 x plus t divided by 120, 1/6, and then 120. And here you have to believe me, because I am not going to spend all the class doing this algebra. So now we have an expression for any hx and time t, which is the one that we need for these two individuals. Okay. So, well, let me write down that function. So this means, come on, that this function is 1 t 120 1/6 and 0. So essentially, for values of x, this is a t. And for x, so this is our function. Let me see if this is 120. So we will have 120 and then 120, and then these two go away. So essentially this would be 1. 1 minus 1 is 0, so that would be the beginning. And then, yes, so that's it. And this is just getting the function that we're going to use to estimate the first moment. So now let's estimate the first moment, which is the life expectancy at hx. That'll be the interval between 0 and the limit that we have here, 120. Come on. Of this function. Well, I should change this because I have t as the limit and s ds. Okay. What can we do here? Well, we have to change. We have to work with a change of variable again. So let's make y in everything that is inside. Which essentially means, come on, that s is going to be, so I'm going to move this, 1 subtracting y, 1 and then, okay. So essentially, by doing this, we have that the life expectancy at age x is the integral when x equals zero, let me see now when s, sorry, yes, is zero, this is zero, so this is one, and when this is 120, then it will be 120 here, sorry, 120 here, and then we can move, so it will be zero, okay? Yes, so let me see. 120, I can move this to this side, and then it's gonna be one, and then I move, yes. Are you following this? Well, the thing is I don't have enough room to go through all this, but let me do it really quick in here. If s equals 0, that means that 0 equals 1 y, which I need to get it in terms of y, so I can move this to this other side, so it's going to be 0. So that means that y is 1, right? And if s equals 120 minus x, 120 x equals 1. I can move this to this side, so I end up with 1 equals 1 y, so I can move this to this side and this to this side, then y is 0. Okay? So this is a just review of Calculus 1 course here, right? Okay. And then what I have is 120 x and y, because y was the thing that is inside, 1/6 y. And this is a constant. I can remove this constant out of the integration, and this will result in, again, here I'm skipping a few steps in this, but it's not that complicated, right? I move integrating this, I add 1, and then I subtract the other value, and blah, blah, blah. So just remember this, okay? So this is the life expectancy. Now, and we're gonna come back to estimate life expectancy for these two individuals. For the variance, we need the expected value of the square of this random variable, okay? So essentially, I'm gonna use here because I don't have much room. So according to the formula that we had before, in here, 2 times this thing. So this will be 2 times the integral between 0 and again the same values. Oh, wait a minute, this should be, no, it's fine, yes. But I think this should be t here. But well, you can follow, right? I was calling this t, so it should, yes, you should change that, but anyway. No, wait a minute. No, more like this, sorry. This is the one that has to be x, and then 2, yes. So this is x, yes. Of, it was 2 times t times tp x, again. I should change the internet. No, I'm just gonna leave it with that. And we follow the same substitution. We made S being Y being 1, subtracting this thing inside. So I'm not gonna solve all this thing, but at the end, you will get the expression to 120 x to the square, and then 6 sevenths, 6 13ths. And that is the second moment. Essentially meaning that the variance for our lifetime distribution is going to be 2 times 120, so it's x squared. I don't know the value of these things, so we could solve for this, and then subtracting 6 sevenths square. Which is kind of a crazy expression, but at the end of the day, it's just replacing values, and we can just, and again, we have some common terms here, the 120 minus x, so I could factor this value out of the expression. I have the 6 sevenths here and here, but again, and we will end up with the square value here, so we could reduce this expression. But let's just estimate the life expectancy for the person who's age 30. So this means that life expectancy for a person who's age 30 is going to be 6 sevenths of 120 minus that. And so that was the life expectancy, the variance of T 30 is going to be 2 times 120 30 squared. Well, if you get this value, you can use this value here. Just replace the values, and you can get life expectancy and variance. Okay. The reason this is really important is that not only we want to know the shape that mortality has, we want to get a general idea of where we're going to be moving in terms of mortality. So that's the reason we need the expected value and then the variance around the expected value, of course. Because if I am working on some projections for my insurance company, I need that variability to be included in my estimations. Because if I just work with a point estimate and something happens and I don't take into account variance, chances are I am not going to hit that value. It could be better if I hit a value of mortality. Well, depends. If we're talking about life insurance, that would be better if I reach a value below mortality. But if I'm working on pensions, it would be better if I reach a value above the life expectancy. So let me see. I had enough room. Okay, so let me write down the expression for 80. And you can get the values. Okay. I think then I have temporary life expectancy. I have another example, but now let's leave it here. Okay. So questions on this? No? Everything cool? Okay. Yes, not for now. That's the that's the spirit. Okay. So if there are no questions, have a nice, well, a good night, a good evening. Enjoy your dinner, and see you on Wednesday. Okay. Thank you.